So welcome back, everyone. It's a real pleasure for me to be introducing Grani Hanasusanto. He's assistant professor in operations research and industrial engineering department at the University of Texas at Austin. Grani received the NSF Career Award in 2018. In general, his research focuses on solution schemes for decision-making under uncertainty, which is the topic of this week's workshop. So he's a real expert in this field. He has application in operations management, energy systems, finance, machine learning, and data analytics. Today we'll be talking, giving the second talk on data-driven optimization, where we're trying to exploit site information. So thank you very much, Grani, for accepting to present the workshop. I hope this talk gives rise to very fruitful discussions afterwards. The floor is yours.
All right. Thanks, Eric. Hello, everyone. Thanks for coming to my talk. I would like to first thank the organizers, Eric, Fabian, and Walter, for inviting me to give a talk in the workshop. So today I will present our recent work on variance-based regularization scheme for data-driven prescriptive analytics with site information. This is a joint work with Pratik Srivastava and Yijie Wang from UT Austin and Chin Pan Ho from the City University of Hong Kong. So I will first begin by explaining the generic problem that we are trying to solve, provide some motivating examples for the problem, and then discuss some of the key challenges in the current approaches. All right. So here we have a stochastic optimization problem with site information. So we have a random loss function, cost function, whose value depends on the decision factor x and some uncertain parameters specified by the q-dimensional factor psi. When making the decisions, the decision maker has access to site information specified by the p-dimensional covariate factor gamma, which influences the distribution of the random parameters psi. So this captures the fact that most decisions in real world are not made in isolation, but rather are influenced by external factors, which are observable to the decision maker at the time he makes the decision. So given the site information, the decision maker's problems is to determine the optimal decision factor x that minimizes this conditional expected cost. Yeah, so you are conditioning on the given site information. So let me provide two examples of classical problems that fit into the framework. The first problem is the portfolio optimization problem, where the loss function corresponds to the negative of the investment return. The decision factor x is the money invested into the different assets in the portfolio. The random parameters for this problem are the rate of returns on the assets, which may be affected by the site information that can include the market indicators, past returns, and even live Twitter feed. The second example is an inventory management problem. So here the loss function corresponds to the firm's total costs, which may include the ordering costs, holding costs, stock out costs, and then faced with uncertain demand represented by Xi here. The firm's decision is to determine the optimal order quantities for each product. And here the site information may include the weather condition, day of the week, some seasonal trends, and many others. We also note that stochastic optimization problems with site information also appear in the context of dynamic programming algorithm for stochastic optimal control problems, where at every backward induction step, one has to optimize conditional expectations of the value function or cost to go function at time t+1, and you condition on the current exogenous state at time t. So there are many relevant applications. So one of the main challenges in solving the stochastic optimization problem with site information is that the exact distribution between the covariate factor gamma and the random parameters psi is seldom known. So instead, what we are usually given is a set of observations based on historical data. Yeah, so the observations comprise n pairs of the covariate gamma and the uncertainty psi. Now, many solution approaches have been proposed in the data-driven setting. We will review the relevant methods here. So the first category is the decision rule approach. So here, note that we make our decision after observing the site information gamma, but before the realization of the uncertain parameter psi. So this decision rule approach seeks for a simple linear or quadratic policy, which is a function from the covariate gamma to the decision x. And the optimal policy, however, is usually hardly simple. Yeah, so the scheme is also less attractive because it is not asymptotically consistent, meaning that as we obtain more sample points, we are not going to eventually solve the problem optimally. The second category attempts to use machine learning, kernel regression, and nearest neighbor techniques to approximate the conditional expectation in the objective function. So our proposed method belongs to this class. The schemes are non-parametric. They don't make any significant assumptions about the joint distribution of the covariate gamma and the uncertain parameter psi. So they're very attractive and they work really well in practice. However, to date, there's an incomplete picture of the schemes on whether they can provide any reasonable out-of-sample performance guarantees. So in this talk, we consider a popular class of regression model called the Nadaraya-Watson, and we will derive its fundamental properties in the context of decision-making with site information. We then propose a regularization scheme that is grounded on the theoretical performance guarantees, and we will derive connections to the recent distribution robust optimization paradigm. So the third category attempts to use machine learning techniques to generate a prediction on the uncertainty. So here, a regression is performed to approximate the conditional expectation of psi given gamma, which is then used to in the optimization model. So the regression technique used can be a traditional one, like least squares, or even a smart one, which takes into account the structure of the nominal optimization problem. And in some of these models, the residual terms from the regression are used as scenarios in a traditional sample average approximation framework. And of course, performance guarantees can be obtained if the true relationship between the random parameter psi and the covariate gamma can be described by the additive error model, where psi can be decomposed as a sum of a regression function of the covariate gamma plus a mean zero error that is independent of gamma. So all these data-driven methods, they suffer from overfitting issues. So some robustification schemes have been built on top of the methods to improve the out-of-sample performance. Okay, so to obtain a data-driven empirical estimate of the conditional expectation, we utilize this Nadaraya-Watson estimator, which is a technique from non-parametric kernel regression that approximates the conditional expectation in terms of a weighted combination of the loss function values associated with the samples in the training data set. So here, each sample I is assigned a weight that is equal to the normalized kernel value for that sample. So that samples that are close to the given gamma, right, the given site information, these samples are assigned higher weights. And in our formulation, we employ the exponential kernel function of the form given here, where h here is a bandwidth parameter. So here we observe that if the bandwidth is very small, then most of the probability mass is assigned to the sample point closest to the given gamma. On the other hand, if the bandwidth is very large, then the estimator here, the Nadaraya-Watson estimator, reduces to the unconditional average, and the problem becomes the classical sample average approximation problem, where the weights are equal to 1 over n. So one of the critical issues with the Nadaraya-Watson estimator is that it is known to be prone to overfitting, especially when only limited data is available. So as can be seen from the examples here, the Nadaraya-Watson estimator, represented by the solid red line, is noisy and deviates quite a bit from the true loss function denoted by the dashed red line. Okay. So in this talk, we are going to develop a regularization scheme that mitigates the overfitting effects, and the regularization scheme is grounded on the generalization bound of, for the estimator. Okay, so we first began by adapting ideas from moderate deviations theory to obtain out of sample guarantees for the estimator. So this gives the result here. And rearranging the terms, we can get this form where we find that for any fixed decision X, the true expected loss, right? The true expected loss is upper bounded by the empirical loss. Yeah, so this is your Nadaraya-Watson estimate plus a square root term that depends on the conditional variance of the loss function in the numerator. And then you have in the denominator, you have the size of the training data set, bandwidth parameter, and the marginal density function G for the site information gamma, at the site information gamma. And here we observe that as expected, the error is large when the variance is large at X. And similarly, the bound is going to be loose when we have few sample sizes. We have few samples. And then the bound is going to be large when the marginal density G is small at the site information gamma. Yeah, so meaning that the covariate gamma is rarely observed. So choosing the best bandwidth parameter that optimally trades off the bias and variance for the estimator, we find that we get an upper bound. Yeah, so the upper bound decays at the rate given here. Okay. So here we see that from the dependence of the dimension P of gamma, we see that the bound does not scale well to high dimensional settings. So in general, this is quite common in settings where kernels are used. We will discuss a way to tighten the bound. But before that, I will first briefly explain how we obtain this result using large and moderate deviations theory. So let me provide a high-level overview of large deviations theory. So here we say that a sequence of random variables satisfies a large deviation principle with speed nu n here and a rate function I if these conditions hold. Okay, so here we have the limit infimum of this sequence of logarithm of probabilities is greater than the negative of the infimum of the rate function over all open sets O, right? Over all open sets O. And similarly, the lim sub of the sequence is less than the negative of the infimum over all closed sets C. So in our context, the Zn here would correspond to the error of the empirical Nadaraya-Watson estimate. Yeah, so it would correspond to this term here. In the traditional settings where your Zn is the the error of the sample average approximation of unconditional expectation. Yeah, so you have average of n IID samples. Then your Vn here would correspond to the number of samples. Yeah, so the Vn simplifies to the number of samples, and the rate I is given by the sort of Fenchel transform of the cumulant generating function of the random variable. In our Nadaraya-Watson setting, we have a weighted sum, right? We have a weighted sum where the weights are normalized so that they are functions of the entire data set. So we don't have average of IID samples in our case. So for most applications, as well as in our setting, the interesting case is when the two infimum values here, they are the same, and the subset Z denotes is chosen so that they denote the failure probabilities. So in this setting, the limit exists, and then just after some algebraic manipulations, we have that the failure probability decays exponentially at the rate determined by this infimum. Okay. So that's a large deviations principle. Next, we look at moderate deviations principle. So here we have another sequence AN. It's a sequence of real numbers satisfying certain properties that I don't show here, that in the limit goes to infinity. Then we say that a sequence of random variables Zn here satisfies a moderate deviations principle if the scaled sequence satisfies a large deviations principle. Now, for such a scaled sequence, the rate function I is often analytical. Yeah, so it depends on the limiting density for the random variables, but not on the individual characteristics of the distribution. So to obtain our generalization bound, we leverage results from Mokadem et al., who proved moderate deviation principles for multivariate kernel regression estimators. And we show that under some reasonable assumptions, which include the boundedness of the support set, and then the boundedness of the loss function, and some differentiability assumptions on the joint density function of gamma and psi, we have that this sequence that measures the error, right, the deviation of the Nadaraya-Watson estimator from the true conditional expectation at a fixed x satisfies the moderate deviations principle with speed nu n and rate function I. And which, as we have seen before, it depends on the density function G and the conditional variance of the loss function at gamma. And this gives us the generalization bound that we saw earlier. Now, in the previous slide, we have seen that the Nadaraya-Watson estimator suffers from the curse of dimensionality, right? In particular, the error decays at the rate given here, where P here denotes the dimension of the covariate vector gamma. So here, let me show how to address the high dimensional settings. So in many real-world problems of practical interest, it is often the case that even though gamma originally lies in a high-dimensional ambient space, it may actually have an intrinsic dimensionality which is much smaller. So to take this into consideration, for our analysis, we consider the setting where the site information factor gamma is drawn from a sub-Gaussian probability distribution and lies approximately in a lower dimensional subspace S, where the dimension is given by P prime and is smaller than the original dimension P. So here we make this sub-Gaussian assumption. It is non-restrictive. It encompasses a wide family of distributions, including the multivariate Gaussian and all distributions with bounded support. And here we make the assumption that gamma S, right, the component of gamma that lies in the subspace S, corresponds to the signal and influences the random cost parameter factor psi, while the orthogonal component corresponds to the noise term, which given gamma S does not provide any information about psi, right? So the conditional density of psi given gamma is the same as the conditional density of psi given gamma S. So taking this fact into account, to obtain tighter error bounds, we propose a dimensionality reduction procedure. Okay, so here we don't want to use the PCA on the entire data set because the resulting sample points will no longer be independent. Okay, so that will prevent the use of moderate deviations theory. And here we develop a sample splitting scheme. What we do is we split the original data set, capital gamma here, consisting of the covariates into two parts, capital gamma 1 and capital gamma 2, each with a constant fraction of points. And then we use the observations in capital gamma 2 to compute the covariance matrix sigma hat 2 and obtain the top P prime eigenvectors. And then we project these eigenvectors in the set capital gamma 1 onto the subspace spanned by the eigenvectors, right? And then we get the projections in the low dimensional subspace, right? So this sample splitting scheme is adopted to ensure that the projected covariates are independent of each other, which is needed for the application of moderate deviations theory to obtain the error bounds. So next, we construct the estimator using the projected data points. And in this case, we are able to prove that the error bound that we obtain using the procedure has a similar form as before, but the original dimension p in the bound is now replaced by the reduced dimension p prime. So this gives us a tighter bound. So now getting back to the non-high dimensional settings. So far we have obtained the generalization bound for a fixed decision X. And now by a simple application of the union bound, we can show that the generalization bound holds for all X in a finite solution set. Yeah, so if we have a finite feasible set for X, then we have a generalization bound that holds for all X in the set. Okay. So here we see that minimizing the right-hand side term implies minimizing the left-hand side, which corresponds to the true conditional expectation, right? So we want to minimize this. In principle, we want to minimize this. Minimizing the right-hand side would imply minimizing the left-hand side, and minimizing the right-hand side furthermore ensures a good generalization bound, right? And we will leverage this idea to formulate an effective regularization scheme. But before that, we mentioned that a similar result can be obtained for the case when the feasible set of your decision X is continuous and bounded. This is done by imposing a Lipschitz continuity assumption on the loss function X. And in this case, we get a bound presented here. All right. So based on the analysis in the previous slide, so an idea that comes to mind to mitigate overfitting to the observations is to minimize the upper bound, which consists of both the expectation and the variance terms. In our setting, that we don't have the true conditional variance, right? So here we have to use the conditional empirical variance. And this gives rise to this variance-based regularization scheme that we have here. We remark that similar ideas have been proposed in the empirical risk minimization literature, where we have a variance regularized sample average approximation for the optimization of unconditional expectation. Now, in general, such a variance regularized formulation is non-convex, even when the loss function is convex in X for all Xi. We will address this later. But before that, we derive sub-optimality bounds on the solution of to the regularized empirical model. Yeah, so we have the solution to the regularized empirical model, and the sub-optimality bound share the same asymptotic decay as the generalization bound. So here we see that the expected cost of the regularized solution is upper bounded by this right-hand side expression that involves the true conditional expectation and variance under the optimal decision X star. Yeah, the optimal decision minimizes the stochastic optimization problem with side information. And here we observe that that if an optimal decision X star has a low variance, right? If it has a low variance, then the second term here is not significant, right? And the last term is going to dominate. And we find that the suboptimality bound decays at a faster rate. Yeah, so we have a faster rate of 1/n(h) to the power p. So this is one of the benefits of the variance regularization scheme. And just a remark that we have similar result for the case where, yeah, so this result holds for the case where we have a finite feasible set, and we can generalize it to the case where we have continuous feasible set. So the regularization scheme, the variance regularized problem is non-convex even when the loss function is convex in X. So when the loss function is piecewise affine, given by the maximum of J affine pieces, capital J affine pieces, we get an equivalent mixed integer second order cone program. So the reformulation is still hard, but can be solved by any of the self-solvers. All right, so this is the second order cone program. Here we denote by P hat I as the weight associated with scenario I, obtained from the estimator, right? Nadaraya-Watson estimator. Here we introduce a decision factor Z. The I component corresponds to the loss function associated with sample psi I. So let me show you how we get to this formulation. So here we introduce an epigraphical variable rho to bring the conditional variance term into the constraint. And then we introduce binary decision variables Yij, which indicates the affine piece J that takes the largest value for that scenario, psi I. Yeah, so that means that Zi will coincide with the maximum value. Yeah, so this is a mixed integer second order cone program that can be solved using any of the self-solver like Cplex or Gurobi. So as a corollary of this result is that when the loss function is linear in X, then the problem simplifies to a tractable second order cone program. We will apply this second order cone program to solve a portfolio optimization problem where the loss function is linear. At this point, we remark that the regularized Nadaraya-Watson scheme that we propose is non-parametric. Yeah, it requires mild assumptions about the joint distribution of gamma and psi, and no assumptions on the form of the optimal policy as a function of gamma. So to showcase the benefit of the scheme, we consider a simple example in portfolio optimization, and we compare against the popular decision rule approach. So in this example, we consider a portfolio of 3 assets. So we have 3 assets, 2 are risky assets, meaning that their returns are random, while the third asset is risk-free. It has a deterministic return of 0. So the random returns for the first 2 risky assets depend on the site information gamma here, and also some residual term epsilon. And then the objective of this problem is to maximize the conditional expected portfolio return given the site information gamma. So here the loss function is linear, and therefore the variance regularized formulation can be solved directly as a second order cone program. And we compare the formulation with a recent regularized decision rule formulation for portfolio optimization proposed in these papers. So here we plot the out of sample portfolio returns against the sample size in the training data sets. So the black curve here denotes the optimal expected return for the stochastic optimization problem with site information. Now the average out of sample returns for our regularized formulation is denoted by the solid red curve, right? Solid red curve here denotes the out of sample returns of our scheme, while the blue curve here denotes the out of sample returns that we get from the linear decision rule formulation. So the left figure here shows that the out of sample returns for our regularization scheme quickly converges to the true optimal expected returns. And in addition, it clearly outperforms the linear decision rule formulation, which essentially obtains the same average out of sample returns as a decision maker who does not consider the site information when making his investments. Yeah, so the the pink dashed line, dotted line here, is the returns of a decision maker who does not take into account the site information. So this is the out of sample returns for randomly generated gamma. On the right figure, we fix the gamma to a fixed value 0, and then plot the out of sample returns for different sizes of training data sets. And here we see that from the two striped lines in red and blue, which record the 10th and 90th percentile returns for the Nadaraya-Watson and linear decision rule methods, we observe that our scheme generates significantly lower variability compared to the linear decision rule approach. And this is because the regularization term encourages a portfolio with lower standard deviation. So just a remark that in this toy example, one can actually formally prove that the decision rule approach will not make use the site information. Yeah, so that's why we see here that the performance is not better than the stochastic model without site information. So the variance regularized model is intractable for a general loss function. Now, to obtain a tractable convex reformulation, we leverage ideas from distribution robust optimization. So here we have a formulation for a generic distribution robust optimization problem. So the model can be essentially thought as a game between a decision maker and an adversary. So the decision maker takes some decision X, and the adversary chooses the distribution P from the ambiguity set script P that hurts the decision maker the most in terms of the expected loss. So here, the decision maker makes his decisions in view of the worst case distribution, right? So this hedges against adverse outcomes. And in some sense, this prevents the decision maker from over-adapting to the observations in the training data, and in turn has a regularization effect that leads to better out-of-sample performance. So usually the ambiguity set is defined in terms of an epsilon, or here lambda neighborhood around the empirical distribution with respect to a prescribed distance d. And when a phi divergence is used as the distance, one can show that the problem is convex. So here we construct the empirical distribution based on the normalized kernel weights that we obtain from the Nadaraya-Watson estimator. And we use the modified chi-square divergence to measure the distance between distributions in the ambiguity set. So we mentioned that some previous papers have looked at distribution robust optimization-based approaches for the Nadaraya-Watson reformulation. However, they either do not provide any theoretical justifications for considering such an approach, or their motivation is somewhat different compared to the work we present here. So our main result here is that the objective of our variance regularized formulation is equal to the worst case expected loss of the proposed distribution robust model, right? Provided that the sample size is sufficiently large. Otherwise, the distribution robust model provides a safe conservative approximation. So this implies that the guarantees that we obtain for the variance regularized model are valid for the distribution robust model. So the analysis of this result follows the approach by Namkung and Ducci, who obtained an analogous result for the empirical risk minimization problem for the optimization of unconditional expected loss. And finally, we derive a tractable reformulation for the distribution robust model. Given here, the reformulation constitutes a second-order cone program when the loss function is convex piecewise quadratic function in X. So now we assess the performance of the distribution robust model in the context of a newsvendor problem with site information. So associated with the order quantity Q and demand Xi, the newsvendor incurs this cost that includes the holding costs when the demand is smaller than the order quantity. And we also have the stock out costs when the demand is larger than the order quantity. So here we consider a two-dimensional site information factor comprising the time of the day T and the popularity of the product P. And this covariate factor is assumed to have a jointly Gaussian distribution with this mean and covariance matrix given here. We assume that the demand varies according to a uniform distribution centered at the random mean C that depends on the covariates in this way. So here, these figures show the out-of-sample expected costs as a function of the training data size. So from this figure, we observe that at points gamma that are further from the mean, they are far from the mean, where the marginal density function value G gamma, remember G gamma for the for this bivariate normal is going to be smaller, right? The regularization scheme is quite effective, right? So here, with a larger regularization parameter, the average out of sample loss decreases significantly. On the other hand, for points gamma that are closer to the mean, for example, for this gamma 4.5 and 2.5, the unregularized model, when lambda is 0, performs much better, right? So this is quite intuitive, since in regions of high density, the Nadaraya-Watson estimator forms a good approximation to the true conditional expectation, even for small sample sizes. By contrast, in the regions where the density values are smaller, the regularization term seeks to alleviate overfitting to the limited data available. Here we also observe that in regions of moderate density values, so for example, for these points gamma, the regularization helps in cases where the sample sizes are smaller, right? When the sample size is small, regularization helps. Okay, so all these results, they are consistent with the generalization bound that we have derived before. So finally, we assess the performance of the distribution robust model in a real-life application of wind energy commitment problem. So here we have a wind energy producer who operates in a day-ahead market and aims to maximize his profit. So at the beginning of day T, the producer determines the wind energy commitment levels for the next 24 hours. And if the actual production falls short of the commitment levels, there is a penalty of twice the respective day-ahead price for each unit of unsatisfied demand. So here, the day-ahead prices are known to the decision maker. However, the hourly amount of wind energy are generated for the next 24 hours are uncertain. Now, as the wind energy is generally highly correlated to the past data, we consider the site information factor comprising the wind energy produced from the previous 24 hours. So these are the out-of-sample statistics of improvements of the different methods over the naive sample average approximation that assigns equal weights to all the samples. We also tested the decision rule approach, but it performed extremely poorly, so we don't report the results. So here we observe that our method generates significantly more profits than the naive sample average approximation. And it also outperforms significantly the unregularized Nadaraya-Watson methods, which itself provides more than 55% improvement over the sample average approximation. We also outperform the recent method by Kanan et al. Here, which assumes that the uncertain parameter psi can be decomposed into the conditional expectation term plus a residual term. And furthermore, we observe that our method is more robust and generates significantly less loss. All right, so that concludes the talk. Let me summarize. Here, we propose a formulation for the stochastic optimization problem with site information based on the popular Nadaraya-Watson kernel regression estimator. We obtain generalization bounds and develop a variance-based regularization scheme that mitigate overfitting issues. We derive tractable distribution robust optimization formulation, which is solvable as a convex program. And then empirically, we demonstrated the effectiveness of the regularization schemes on 3 applications in portfolio optimization, inventory management, and wind energy commitment problems. So that concludes the talk. Thank you so much for your attention. I'll be happy to answer your questions. Thanks.
Thank you very much, Grani, for this excellent presentation. There's already a question in the chat. Sven, do you want to voice your question, or you want me to read it?
No, I can ask it. It's not very it's not a really critical question, because this concerns more the efficiency of how you solve the problem. On page 27, you had the mixed integer second order cone programming formulation, and it uses what's normally referred to as a big M formulation, which is has notoriously poor relaxations, in the sense that you will almost all the binary variables will come out fractional, and then you search a massive branch and boundary. There's been some work there by some people, including Jeff Linderoth and Dr. Gunlock and Frangioni and other people, who looked at what's called a perspective formulation that's potentially a tighter formulation. So I don't know if this turns out to be a bottleneck in your application or solves slowly, then there's potential for making it faster by changing the formulation. And
yes, definitely. That is something that we should investigate. Yeah, we
but
I
don't know how slow this is. I mean, if this solves quickly, then ignore my comment. I mean, if you can solve this in a second or two, then it doesn't.
You're actually right. So this is not scalable. We tested on moderate size problems, and it doesn't solve that fast. It's not that efficient to solve. And then we don't really solve that problem anymore, because we have the distribution robust model, which essentially provides the same performance, right? And but that is something that is definitely we should investigate. That will be interesting to implement this relaxation scheme to solve large-scale instances of the mixed integer second order cone program here. Yeah, thank you.
Thanks.
Any other questions from the audience, participants? I see there's one question from Eugen Han.
Hello. Okay, do you hear me?
Yes.
Okay, good. Okay, thank you very much for your interesting talk. I also have a question on this mixed integer SOCP formulation that I can see right now. So as far as I know, you also have some nice, interesting work on like a co-positive programming and completely positive programming. So I was just curious if you had any chance to try to reformulate this non-convex problem as those kind of problems, or any approximation through those techniques.
Right, yeah. We didn't really investigate that direction. So definitely you can get a co-positive reformulation for this kind of problem. Actually, you will get a completely positive program, and then the completely positive program, you can actually get a relaxation. The relaxation is a semi-definite program, which from my experience, it works really well. The semi-definite approximation works really well, but of course, a semi-definite program is not that scalable. you can consider weaker approximations. So you can actually develop weaker approximations to the completely positive program in the form of second order cone program. Yeah, so not mixed integer, but just second order cone program, which is tractable. The approximation is weaker and it can be solved efficiently, but I don't know yet how bad the approximation will be. But that's also another interesting direction. Yeah, thank you for that.
Yeah, so my empirical experience on solving like mixed integer SOCP, especially with these big M reformulation, was not very tractable, not very efficient. So I was just curious. Thank you for your answer.
Another idea that we also thought at the time, so we have a sort of second order cone, right? We approximated the second order cone here with basically here we have a 2 norm, right? We approximate the 2 norm with a 1 norm upper bound, and that can be solved faster. That can be solved faster, but we tested on moderate size instances. It's still too slow for us. Yeah, so for this kind of problem, the wind energy commitment problem, the mixed integer program does not solve that fast. It's not so efficiently solvable. So we decided to just use the distribution robust model at the time. Yeah.
Okay, I see. Thank you.
Yeah, we have another question waiting from Utsav Sadana.
Hi, Grani. Nice presentation. I have a question regarding like we have an approach where we try to determine the decisions as a function of the features, and then we have approaches like this ND regression estimates where we are trying to determine a conditional expectation. And do you think that the approaches where we are mapping, we are trying to determine the optimal policies as a function of the feature space, these approaches could help us guide in determining the good features that could be useful for the problem? Because the question that interests me is, how do you determine the features which would be ultimately useful for determining the optimal policies?
Right. So you're talking about the decision rule approach, right? Where you have a policy as a function of gamma.
Yes, I mean, my question is more related to how to determine the features which could be useful for determining the policies, rather than features which could help me in determining a good conditional expectation for the problem. So
I think he's referring to the dimensionality reduction that you presented and how to select the features. Right now, I had also this observation that by doing PCA, you don't really model or try to exploit the relationship between gamma and psi.
Right. Yeah. So in this case,
maybe have you explored other ways of doing this dimensionality reduction that would take the objective function into account? Is that the question you're referring to, Utsav?
Yes, yes. Yeah, I mean, mostly from the perspective of using policies which could be optimal.
There's this work by Paul Grigos and Adam L. Maktub, where they actually perform some kind of a regression on psi given gamma, but they also take into account the structure of the optimization problem. So you can do that. In that case, you know, you will get you kind of get a prediction on the features that will be most relevant to the problem. But unfortunately, that problem is difficult to solve, right? To perform the regression is something that is difficult to solve. Basically, trying to incorporate the structure of the optimization problem into the prediction model, it would lead to a difficult optimization problem. It may not be solved easily. So I believe in their paper, they consider as the optimization problem, you know, the loss function is just a linear loss function. Yeah, so the L here is just a linear function where the coefficients of your X is uncertain. Yeah, so but in general, that would lead to significant intractability, I believe.
Thanks. I can follow up if there are no other questions on. I don't want to hijack the conversation.
I don't see any other hands raised. So
Okay.
as long as there's no more hands raised, this is the conversation.
Okay. So I understand in the paper that you are mentioning about Grigas and El Maktoub, they also don't talk about what features to take. I was more referring to the paper by Ban and Rudin, where they have these two approaches where they also use the ND regression estimator, and as well as they map the policies from the features. And they try to determine the policies as a function of the features. So these two approaches look different to me in some way, and so I was thinking that is there a way where one approach could guide the other approach towards determining the optimal policies, because I couldn't find a reference where the literature is focused on determining features which are useful for determining the optimal policies.
I see. Yeah, that's an interesting idea. So in that paper, they're searching for policies, right? They're searching for policies from the site information, gamma to the decision X. And in their case, they have to restrict the hypothesis space. So they consider a sort of a smaller hypothesis space, for example, linear policy or quadratic policy. And you can actually solve the problem tractably. But the issue is that you will not be able to solve, you will not eventually solve the stochastic optimization problem with site information eventually as you get more and more data, because you restrict the hypothesis space. But perhaps what you could do is you could potentially expand the hypothesis space as you get more and more data. And in that case, you also get some kind of asymptotic consistency. But then at the same time, when you optimize for a finite data size, you also get a good policy that that takes into account the best feature.
No, I think I find it's interesting to try to see strengths and weaknesses. Perhaps what Utsav points to is you could use the decision rule approach and impose some sparsity on it to identify a pattern of dimensionality reduction or something like that, just to highlight what are the features that are the most relevant.
Right.
And then perhaps use a kernel density estimation on the subspace spanned by these features or something like that.
Yeah. I think that's
something to try on a problem. Any other questions? No questions. One thing I just wanted to comment on this. It's been a long time I've worked on that paper with Thierry Bazier-Mat, but one thing that was really important for us back then in our mind was that when we get these bounds, you mentioned somewhere how the bound is related to the size of the feasible space, right? The norm of calligraphic X or some cardinality on calligraphic X.
Right.
And we were feeling that we were arguing that the size of feasible space is dependent on P typically. So we have a whole section of that paper where we say as you increase P in these bounds, you have to do something about the feasible space also. Because
perhaps in that application, portfolio optimization, the dimension of your decision scales with the dimension of the random parameters, right?
Yeah. I mean, we were doing these decision rules. So in the end, I think the decision space was the terms of the inner product. So it was scaling with the number of side information. But in your and indeed, like perhaps if you have more stocks, you'll be using more data, to, or the other way around. So there's and sometimes these bound, they hide this interaction between the dimension P and the dimension of the feasible space.
Right.
Side comment. Any other questions or comment about the work? I feel like it's really nice to have had Guzin's presentation and then your presentation, Grani, in the schedule. You sort of both argue that each other are doing the wrong thing. You use her method and say that your kernel method is slightly more robust, or
yeah, it's not wrong. It's just that in that real life application, you cannot actually decompose the random parameters into the regression function and residual term. Yeah. So in this application, you don't have that relationship, right? So you cannot get psi t is equal to psi expected value of psi t given psi t minus 1 plus a residual term. Yeah. So if this assumption holds, then I believe this method works really well. Right.
Okay. Well, if Guzin is there, perhaps we can follow up on these discussions and debates during the break. I'm curious to know her opinion. This being said, since there's no other comments, we might as well close this session, this presentation.